Hello everyone, my name is Mohammed and this is my Computer Technology Project 1, Progress Video 1. And my supervisor for this project is Dr. King Sung. So, what is my project first? My project is an FPGA based timing ignition module. A little bit of background is that I have a motorcycle that I've been restoring. It's from 1982 and I want to kind of create a little bit of logic to kind of reverse engineer, create a new one, and improve it. And it's just a good gateway to get me into creating more professional designs. So before I get ahead of myself, let's look at the project overview. What does an ignition timing module do? So what a timing ignition module does is that it from the signals it gets from the alternator or the crankshaft sensor, it will tell the piece of logic which angle the crankshaft position is, or the what at what stage of the engine of the cylinder is in. So whether it's at an intake, compression, power, or exhaust, and you kind of deal with the and that kind of this board just kind of takes those signals in, calculates it, and sends that spark in. So the next question is why is the ignition timing important? So the ignition timing is important is because if it sparks at the intake, that's too early. What can happen is a misfire can happen, rough running, and or the engine might not even run at all. If it's too late, it could what it could do is could flood the cylinders. Generally, though, those are not bad if they happen in a short time, but if it's ran like that for a long time, it's not good or it's not healthy for the engine. So that's why it's kind of important. It's really important to get it bang on. And the final question is, why are we using an FPGA? Why can't we use a microcontroller? So the reason I'm using an FPGA is because I really want to learn it. This is kind of I've been really interested in this technology for a long time now. I've got my foot in the door during an internship, and I've taken a lot of units with that uses FPGAs. And now let's actually get to the real reasons why you'd want to use something like an FPGA versus a microcontroller. Well, generally an FPGA, it's uh, it's more accurate in terms of timing wise. It's you can do more stuff that's a lot faster. Um, it's more versatile, and yeah. Generally those are the three things compared to a microcontroller. Because microcontroller will always be stuck in this kind of four-step process of the fetch, decode, execute, store cycle, and most microcontrollers are RISC architecture. So any of those four functions, they can take more than one clock cycle, and you can't actually guarantee the timing. If you try to make an LED blink on and off every second, what will happen is the LED won't be blinking the exact time period. So usually, what microcontrollers does is they include special circuitry called timing modules within the SoC or the microcontroller like processor chip itself, and that usually handles like if a FPGA has a PWM signal output or a PWM pin, that one pin can only do it because of the circuitry behind it. And generally, it's in terms of peripherals and I/O, it's not as flexible as an FPGA. So I could just this is kind of the stuff I want to learn, and I find it really cool, especially of how fast and how parallel an FPGA can be compared to a microcontroller. So, what are my project objectives? So the first thing is I want to be able to interface with a 12-volt system, learn how the learn the circuits of the from the 12-volt signal down to 5-volt and vice versa. Learn all of that. The second part is power distribution networks. So how is an unregulated 9 to 14 and a half volts can be regulated to a 5 volts. The next bit I want to learn is PCB design. So this part I really wanted to learn for a long time, but throughout my studies I realized that PCB design is not within one of my units. So I thought this would be a cool way to actually get a little bit of experience in making a PCB, printing it out, ordering it, bringing it in, and seeing how well I've done. And the final objective is to actually test on my motorcycle and ride it and see how well it does compared to the original or compared to others. Now, what I've done so far within the first couple of weeks, I started to learn about voltage regulators and power supplies. So the why power supplies in particular? Well, generally, I thought about power supplies is they convert. The first thing they do is they convert, I think, a 240 volt AC to a DC voltage, but that's generally still too high for regular computers. And then they keep on stepping it down until it's a stable signal usable for the whole computer, for the graphics card, CPU, and all of that. So I had one laying around, and I opened it up, and I started looking at the circuits. And there's one chip that kept on popping up over and over again, which is a voltage regulator. So what a voltage regulator circuit kind of uses the voltage divider circuits to actually sample the input voltage versus the output and steps down the voltage into a reliable into a reliable signal or reliable power. And the way it does that is by turning on a gate and then closing it off over and over and over again. And when you actually first observe the waveform outside, it'll be very, very choppy. And the way the power supplies actually get rid of that choppiness is by adding some not resistors, some capacitors. And by capacitor holding a little bit of charge, what you can do is you can get an average, like constant voltage. So that's kind of what I've implemented. So here is the LM2596, which I've looked at, and I've looked at different designs and different modules that are available. So generally, this is the chip that hobbyists use, but I've been looking at also different grades, and the way it works is the exact same thing as I explained it earlier. And this is kind of here how I've kind of implemented it with a slight change. So with this one, it's all fixed resistors. This is called a fixed voltage regulator. All it does is it always outputs to voltage. The one I have here is a dynamic one. It can grab signal. It can grab any signal from, I think it was 6 volts all the way up to 32 volts, and it can actually give you a range of voltage outputs depending on that second resistor on the voltage divider. So here in my oscilloscope, what you can see is a signal going high, going low, and doing that over and over again. And then this is the 4.7 volt output, which is done pretty well, as you can see what I've measured so far. And that's what I've kind of done so far. I've still have to look into it a little bit more, but so far I think the power side of the circuit is pretty good. Now, what are the main challenges? So, the biggest challenge in creating this project is rule of thumb. Like, generally, when you look at a PCB, especially when it's interfacing with the outside modules, there's a bunch of more circuitry than just connecting it directly. What are those rules of thumbs? What do I have to learn? What is the stuff what are the things I don't know? So throughout this whole period, I'm gonna have to learn and find out what is how do I make a reliable PCB? That's basically it. So electronic risk is if I don't do the first step well, it could fry my PCB. It could fry my FPGA chip. It could do any amount of damage. So I have to make sure that these two are very accurate. Now, why timing accuracy? I just said earlier that FPGAs are very good at timing. Well, that's kind of this thing I give up in an FPGA. So microcontroller, very easy to program and it's easy to test. With an FPGA, it's extremely difficult to test. So within FPGA, there's a development period of actually making the module, and that's like 25% of the development period, and then another 75% is testing the actual module itself. So there's two types of testing. There is the self-checking tests where you write a program and you simulate this whole big module, and based on the signals you input and X amount of clock cycles, this is the output that you get. So that's kind of the self-checking test benches. That's what they call them. The other way is manually seeing. Is to have a big truth table and seeing this is my input. This is my expected output. And if anything goes wrong, where does it go wrong? And that's kind of like the biggest hard part. It's not like code where you can debug and do line by line debug. With an FPGA, it's a little bit more complex than that. You have to do a lot of like tricks to actually get the right output and actually debug it properly. And the reason for that is that everything's ran in parallel. Everything is ran at the same time. So a good FPGA hierarchy architecture will help the timing accuracy and the validation of the actual module. Now, the conclusion. So, what are my next milestones? So, even though it sounds like I've done a lot for my first couple of weeks, there's still quite a bit left to do. So, my next milestone is actually picking the components. What components am I going to be using? What pins are available to me? Um, I'm gonna. I've applied for an Altium Designer license, so I can actually start practicing my PCB design. I've enrolled in the Altium Designer education program, and I'm gonna go through that whole program so I understand all the functions, how to import the schematic, how to import the module, how to make a Gerber file, and all of that. And I think that's where what my progress video 2 will actually explain. Anyway, thank you so much for listening to me, and this is the end of my progress video 1.